Cuma satu grup ya Pak yang dilihat?
Ya Pak?
Satu grup aja ya?
Yeah, as a group first.
Okay.
Later we will call them one by one to the breakout room.
Andi bisa share screen?
Oh, wait.
Good afternoon, Pak Dedi, Pak Kolis, and friends. So today we are going to be presenting about our PKM project entitled Synthesis of Polylactic Acid from Banana Hump as the main material of biodegradable surgical suture. Next. So what is surgical suture? Surgical suture is a medical device which has a... sorry, sebentar, sir. Sorry, sebentar ya, sir. Ini... Okay, I'll resume. So as a medical device which has a function to seal tissues, and due to its function, it is commonly used in hospital by the doctor, and it is also versatile. It means that it could be used in many applications from small wounds to big wounds to operation and that kind of stuff. So one characteristic that is important for a surgical suture is it should be biocompatible because it is implanted in the human body. Therefore, yeah, it should be compatible with the human body and also the organs inside, so that there will be unexpected responses coming. There will be no unexpected responses coming. Next. So as we have all already known that Indonesia has a very high population, which means that the tendency of people getting into accident or people that need surgical suture for their treatment will also be high. But the problem is 94% of the surgical suture in Indonesia is still imported. And due to the high demand that we need, it will also lead to a high cost, which is why this is one of the reason why we are doing this project. Next. So our aim is to produce a biodegradable synthetic suture out of naturally derived material. So why biodegradable? Because it will be also less cost for the person that will use the surgical suture, because it could be absorbable by human body. So it wouldn't need to be taken off from their body. And why naturally derived? That is because in Indonesia has rich natural resources, and that's why we want to make use of those natural resources. So it will also leads to a low cost of production. So we are using PLA from Banana Hump. Why Banana Hump? Because it is abundant, and by using Banana Hump, we could also decrease waste coming from banana trees. So what we are going to use from the banana hump is the starch. The starch could be converted into PLA by a series of by some procedures that will be explained later. And PLA is proven to be biodegradable and also biocompatible to the human body. Next. So there was a research that had been done that assessed the characteristic of the PLA sutures. So the PLA sutures that these researchers made, the source is below, but I think it couldn't be seen totally, ketutupan. And they made PLA sutures, and then they also they characterize their PLA sutures. The sutures have a size 5.0 based on USP, or United States Pharmacopoeia. It has a tensile strength of 12.5 Newton and not full tensile strength of 7.33 Newton. So as we can see from the table, the left picture, the one that I squared, that's the tensile strength of other sutures such as polyglycolic acid (PGA), polyglactin or vicryl, PG, and PGC is polyglycolide caprolactone, if I'm not mistaken, and they are all absorbable. They have a mean tensile strength of around 8 newtons. So it means that the PLA switcher could also is also as reliable as other switcher. And also on the graph at the picture on the right side, it's the not full tensile strength of also suture of size 5.0 in collagen sutures and also synthetic sutures. And we will focus more on the synthetic sutures because our PLA suture is categorized as a synthetic suture. As we can see, the value is 6.67, and the not full tensile strength of the PLA suture that had been tested by some researchers before is 7.33 Newton. So it also means that the PLA suture could be as reliable as other suture. Next.
Now we're talking about the basic principle of this for this experiment. So our experiment is have three references. So the first references that we use is about the synthesis of bioplastic polylactic acid from mangrove fruit, Soneracia caseolaris. So the aims of this paper is to create a synthesis of bioplastic that can be substitute so the usual plastic can be substituted to this bioplastic from mangrove fruits, and we follow the step that they use to create the polylactic acid. And the second paper is about the made of the sutures from eceng gondok, and the aim of this paper is to study the effect of polymerization reaction time on PLA yield and the effect of PLA to glucomannan compositions on the mechanical properties of the sutures. And the third paper is about the optimization of the making of polylactic acid without catalyst. And the reason why we use this paper is because basically it shows that the step where we don't have to use catalyst, and the aim of this paper is to measure the optimal temperature and time for the formation of the metallic molecules. Next. So now we're discussing about the one by one equipment that we use, materials that we use. So the first one is banana tree. So banana tree is a monocot plant, and there are a lot of benefits of banana trees. For example, is the root can be used as a medicine for anemia, scabies, leprosy, and skin disease. And fruit is also can be used as tonic, diarrhea medicines. And also for diabetes and other stuff. And the third is the flower. The flower can be used for dysentery medicines, diabetes, and other menstruation medicines. And the stem can overcome anti-inflammatory pain and snake bites. And in this paper, we focus on the stem, and the stem is actually there are two stems. The first one is a pseudo stem, and the second one is the real stem, or we can call it banana hump, because in the real stem, it has 76% of starch and 20% of water, and the rest is about the is filled with vitamins. So we use the hump because of that reason. So the, when we compare one banana trees to another banana trees, we found that kapok banana trees has high carbohydrates than other banana trees. Next. So now is about the glucomannan. Glucomannan is basically a polysaccharides, and it composed of 67% of the mannose and 33% of the glucose. And this glucomannan possesses high viscosity and elastic properties. So it can be used as thickener, or it can improve food textures. And this glucomannan can be found in tubers such as porang tubers, and also some fruits like salak, especially in the seed. So next is the polylactic acid. So for the polylactic acid is a part of polyester aliphatic family, which composed of lactic acid monomers. And this polylactic acid is famous for the characteristic which is biodegradable and also biocompatible. And polylactic acid can be made from starch through several steps. For example, is starch isolation, hydrolysis, fermentation, and also polymerization. These steps that we will take this step to make the PLA. And the commercial PLA for sutures has a molecular weight of 50 to 200 kilodalton. Next. So now we're talking about the hydrolysis. So hydrolysis, as we know, it will produce the byproduct is water from one big molecule into two other small molecules. And the hydrolysis that in this experiment is the big molecule is the starch, and it break down into maltose, which is disaccharides, dextrin, and also glucose. And this hydrolysis can use enzyme and acid, but the enzyme is can cut specifically. However, the acid cut random can do random cut. But in this experiment, we use acid. Next. Next is about the fermentation. The fermentation is an anaerobic process by using enzyme from microorganism to break down complex molecules, complex organic chemicals to be simpler products. And the enzyme that is used to hydrolyze big polymers to be simpler monomer like carbon dioxide and also acid. Next is about the polymerization. So polymerization is a process where it combines monomers from into one large molecular structure, one large chain. So in the polymerization, there are two types. The first one is condensation polymerization and also the addition polymerization. As we know, the condensation polymerization means that it will release small molecules like water, and in addition, it combines the monomer without releasing water or small molecules. Last is about this wet spinning. So we use this technique is because it is simple and it is inexpensive. And so basically the wet spinning is a technique for spinning yarn from polymers. And the wet spinning used for polymers that are not melted and can only soluble in non-volatile or thermally unstable solvents, and it can only be removed by chemicals. And so how does it work will be explained by Angeli, but I will explain it a bit. So the polymer will dissolve in the solvent, and the solution will be frozen in the ice bath, so it can um, form like fiber. So it it can be spinned uh, and created fibers like that. Next.
Next, we will talk about the materials and fabrication. First, here are the list of equipments that we use. And next, these are the list of materials that we use. Next, and now we'll talk about the processes that will be done. There are six total processes. The first one is starch isolation. Once the starch is isolated, it will be hydrolyzed to produce glucose. And then next is the glucose fermentation process to produce lactic acid. And then this lactic acid will be polymerized to produce polylactic acid. And once the PLA is obtained, it will be characterized, including functional group analysis and molecular weight measurement. Last, the suture will be fabricated using the wet spinning technique. Next. For the starch isolation process, first the banana hump that is collected will be cleaned and chopped into smaller pieces. And then the smaller pieces will be soaked with water and natrium metabisulfite with the scale of 0.2%, which means for every liter of water, there has to be 2 grams of natrium metabisulfite, and it will be soaked for 30 minutes. After that, The small pieces that has been soaked will be dried under the sun and then mashed into smaller piece into powder before it is strained using a 60 mesh sieve. After the powder is formed, 50 grams will be taken and then mixed with 100 milliliter of aquades and left for 24 hours. It is left for 24 hours to produce the suspension. The suspension will contain starch and it will be filtered and then dried. It will be dried under the sun just like before, and for further drying will be inside an oven for 60 minutes at 80 degrees Celsius. And once it is dry, it will be mashed again into powder and then strained again using the 60 mesh sieve. Next. Next, the starch that is produced will be hydrolyzed. So first, we will take 20 grams of starch and mix it with 450 milli aqueous. And this mixture will be magnetically stirred. And once it is homogeneous, hydrochloric acid will be added gradually until the pH is 2. After it has reached the pH level of 2, it will be placed in an oven at 80 degrees Celsius for 60 minutes. Next is the glucose fermentation process. So from the glucose that has been obtained from the previous process, 10 milliliter will be taken in an Erlenmeyer flask, and then it will be added with 1 test tube of the bacteria, which is the Lactobacillus bulgaricus bacteria. And then this mixture will be incubated for 8 hours at 45 degrees Celsius. Once the incubation process is done, 90 milliliter of glucose solution will be added to it, and then it will be incubated again for 8 hours at 45 degrees Celsius. After this incubation process, glucose solution will be added again, this time 900 milliliter. So there will be a total of 1000 milliliter of incubated solution. And from this total, 150 milliliter will be taken and then added with 1500 milliliter of glucose. And then this solution will be incubated for 72 hours at 80 degrees Celsius. We must also make sure that at every incubation step, the pH is equals to 5, and if it is not, we must adjust it by adding an AOH. Next is the polymerization of lactic acid. So from the lactic acid that is produced in the previous process, 100 milliliter is taken, and then it is heated at 120 degrees Celsius for 1 hour. And then next, it will be further heated at 150 degrees Celsius for 24 hours. And then the obtained PLA will be cooled in room temperature and then dissolved with chloroform. After it is dissolved, the sedimentation process will be done with the help of methanol. And then the sedimented PLA is dried until the powder is formed. Next. So the PLA that we obtain will be characterized. The functional group analysis will be done by FTIR, which is Fourier Transform Infrared Spectroscopy, while the molecular weight and PLA yield measurement will be done by first calculating the viscosity of PLA. So the PLA sample is dissolved in ethyl acetate beforehand with the variation of concentrations of 0.1, 0.2, 0.3, 0.4, and 0.5% at 25 degrees Celsius, and then put in the Oswald viscometer. And then to calculate the viscosity, first we calculate the relative viscosity, which is equals to the time taken by sample to pass through the Oswald viscometer divided by the time taken by the solvent. Then we'll calculate the specific viscosity, which is equals to relative viscosity minus 1. And then we calculate the reductive viscosity, which is specific viscosity divided by concentration of PLA. Next, we plot the intrinsic viscosity by using the PLA concentration as x-axis and reductive viscosity as y-axis. And then the molecular weight can be calculated using the Markov equation, which is intrinsic viscosity is equals to K times molecular weight to the power of A. The K and A values depend upon solvent and temperature when the experiment is done. In our experiment, we use ethyl acetate solvent at 25 degrees Celsius, for which the value of K is equals to 1.58 times 10 to the power of -4, and the value of A is equals to 0.78. Next. Plus, once we already characterize the PLA, we will move on to the suture fabrication, which is the wet spinning technique. So the materials, which is PLA, will be dissolved with chloroform, while the glucomannan will be dissolved with water. And then these two solutions will be mixed with the ratio of PLA to glucomannan equals to 3 to 1. And then this mixture will be loaded into a syringe pump. The syringe pump is connected to an aluminum tank which contain solutions such as isopropyl alcohol, short alkenes, which we use is hexane and heptane, isopropyl alcohol, PEG, and amphiphilic polymer. And then once the syringe pump is turned on, the mixture will be sprayed onto the aluminum tank. So these solutions inside the aluminum will coagulate the polymer, which will form the thread. And once the thread is formed, it will be pulled out of the solution and rolled onto a spool. And after the thread is already formed, meaning that once all the material is already used up, already formed the thread, the obtained thread will be kept in a freezer at approximately -20 degrees Celsius until it is needed. Next.
So let's move on to the results and discussion of our experiment that we've done. So as Anjali explained before, there were 6 steps, and from what we've done, we have done step number 1, which is the starch isolation, and the step number 2, which is the starch hydrolysis, and that will be further talked. So now let's move on to the results of our experiment. So as you can see from number 1, it is the kapok banana hump that we use, and that is just one of them, and it was cut into pieces, and as you can see, it is shown at picture number 2, and then after it was cut into pieces, it was drowned for around 30 minutes at the water, at distilled water. And it was added natrium metabisulfite in the water, and it was exposed by sunlight for around 7 hours, and actually the result was not quite dried well, so we put it in oven at 60 degrees Celsius overnight, and then we get the nice dried pieces, and those dried pieces were made into the powder, were blended, and we get the the powder, and then the powder was sieved using 60 mesh, were strained using 60 mesh, and then the powder that we have sieved then we'll be using it for the next step. And these are the steps that we've done before the milestone, the biomaterial milestone before. And the picture number 7 was our result, and it is not there yet. It is not finished yet. And as you can see, there is the label of the first trial and second trial, and it shows different color because for the second trial, I think we get wrong at the over the drying part, and it we think that it affect the color, but it shows a quite dry result. And then for the our further development before at the biomaterial milestone, we will be finishing the starch isolation, and which is that we actually did it. And the powder that that was mashed, that was strained before, were put into the water, distilled water, and it was um, live it live and it was and we lived it for over a night. It is not over a night, it is actually 24 hours, and to make the suspension. And then the result were put into an oven place, as we can say, and then the the starch then put exposed put where there is sunlight, and it was exposed by sunlight. And then after that, the starch then put into an oven for 80 degrees Celsius for 60 minutes. And then it was crushed using mortar. And then it was then strained again using 60 mesh strain sieve. And this is the first step, the starch isolation. It was done here. Then after that, we were planning on finishing the next step, which is the starch hydrolysis, and we did it, where the product before, the powder before, was then dissolved in water with a ratio of 1 to 22.5, which is the starch is 1 and the water is 22.5. Then it was dissolved, and after it was dissolved until it is homogeneous, then it is added with HCl gradually, as Anjali explained before, until pH 2. Then after that, it was heated at 80 degrees Celsius in oven, and then cooled it, and then we get the glucose. And for a starch hydrolysis step, we stopped right here. And this is the result shown in picture number 2. So for the next step that we want to do, first we will repeat the starch hydrolysis, because we just produced one liter of it. So, and we need 2,500 milliliter of it. And another from that, it is to move on to the next step, which is the fermentation. But as we know that the condition is not friendly to us, which makes us can't do our experiment, but we still want to try to find the best solution. Either can we do it at home, or perhaps we could make the DIY and incubator, or we borrow it from the lab, which is the step number 3 here, so that we could do the fermentation step. So the information was actually informed to us this morning, so we want to find the solution. We want to have uh, talking to each other, yeah, and at this evening, so that what we will do next for further details. And to conclude our presentation, so the biodegradable surgical suture will be fabricated from PLA, and it is made from Banana Hump, which is our main, what we can say, main materials. And the PLA is created through hydrolysis, fermentation, and polymerization. The PLA will be characterized based on viscosity and chemical structure, and then the PLA and glucomannan will be wet spinned to form suture. That's all from us. Thank you.
Okay, thank you, Ezra, Grace, Angeli, and Adi. So I would like to request Pak Khalis to throw some questions.
Okay, thank you. Very nice topic, very interesting. And I have so many questions actually. There is one interesting fact that you mentioned about the mangrove, that actually exactly the same mangrove that I use also for my research, yeah, Soneratira solaris. And also, in fact, I just submitted proposals together with our colleague from New Zealand for bioplastics, Pak Dedi, from Indonesian Biodiversity, ya. Jadi pas banget ini. Jadi just for information, Sonetria solaris ini have a very potential for anti-MRSA activity, ya. Okay, but that's not what I'm going to ask you. You mentioned about molecular weight, how important the molecular weight is, because this is a polymer, right? So you can basically make short or even moderate or length polymer. Am I right? I mean, anyone can answer this question, right? So you mentioned about 50 to 200. Can you go back to the previous slide about the molecular weight? Because I think this is important for the strength and everything, the characterization. Yeah. Mana yang ada molecular weight-nya? Kayaknya tadi ada ya.
PPLA.
Okay, yeah, kilodalton. Okay, 50 to 200 kilodalton. Oh, okay. You use kilodalton. You know that usually kilodalton means usually used for protein, right? Do you know what kilodalton means? The size is kilodalton. What does it mean? Anyone can answer? And how you make sure that you got the right size for this PLA, because this is polymer. It means it can go on and on. It depends how your procedure is.
I've searched the internet just now, and I think 1 kilo Dalton is equivalent to 1 gram per mole. Gitu. So if it's 50 until 200 kilo Dalton, it could also be considered. It could also be set as 50,000 gram per mole, something like that.
So how you later on, how you in the process, how you make sure that your size of the PLA is according to the size? What really make the difference? In what step that you can really play around with? No, I'm really asking because I don't know much about this.
It's in the polymerization step, because that determines the molecular weight. Actually, it basically people usually use ring opening polymerization because they said that it is they can control the molecular weight with that. However, because in our lab we don't have the tools, and we ask about it to Kak Tablik and Kak Ijal, and they said that they don't have the equipments that we need. So we change it to the condensation polymerization, and we did it without catalyst. So we playing with the heat and the temperatures and also the time. And we found when I read in some papers, they said that if it is we need high temperatures to make the molecular weight become higher. However, don't be too hot because it will evaporates the lactic acid, and for the time, don't be too long because that will evaporate the lactic acid and make it go
Do you
soft.
have the exact number when you said don't be too hot, don't be too long?
In the
Roughly,
paper,
yeah,
in the
according to
paper, it's like
literature.
160 degrees Celsius. It's an optimal temperature for that, for polymerization. Um,
And the
yeah,
duration
the
is
PLA.
24 hours gitu.
24 hours. Okay.
There has been a paper, and a researcher had proven this gitu. Had tried this experiment.
Yeah, because it eventually at the end it will be very important for you to characterize that you got the right size, right, of this, because it will relate to the strength of the fiber and so on, right?
Yes.
Okay, so do you know, can you explain about FTIR that you are using to characterize the polymer? Do you know anything about FTIR? What does it stand for and how does it measures? And what functional group that you are looking at? Saya boleh nanya banyak kan pada dia?
Boleh Pak, boleh silakan. You have time.
So ada mau yang lain jawab dulu atau gantian aku?
Ya, gantian lah jawabnya.
Atau mungkin nambahin aja. So FTIR is the types of spectroscopy. The longer name is Fourier transform infrared spectroscopy. So it's used infrared. So by using that, we can know the functional groups by knowing the apa namanya? By using
Absorbance, wavelength,
yeah, absorbance.
and absorbance.
Okay. From the structure, what kind of functional group do you think it will be there?
Anjali
You see the
Andi,
structure, right?
Anjali Andi, ya boleh jawab.
Ya, gantian jawabnya.
Gantian.
Yeah.
So you know the structure, right? You show us the
We're
structure,
looking
right?
for
So what are there? What is the functional group? Do you know what functional group means?
They should know because they already have organic chemistry.
Yes.
Yeah, they should.
so we're using the FTIR to confirm if we actually get the polylactic acid, right? So
Okay, I'm asking
we
you
will
about
be
the
looking-
functional group in the structure. At least you can mention at least 2 here. Or yeah, 2 there is. Is it an acid or a ketone or a alcohol or anything? You know about the functional group, right? Because in the IR later on, it will have a specific value for different types of functional group. That's the way how you characterize the structure.
So there will be the OH group, what's the name? Hydroxyl group.
Okay,
The
group.
OH
Yeah.
and
Okay.
And the double bond.
And also
C double bond O. This is carboxyl. C double bond O. Is it carboxyl?
Well, do you know?
No.
You know the substance, right? Is it an acid or is it what? Lactic acid, right? So it should be a carboxylic acid, right? Yeah. From the name, you should know already. Yeah, it tells by itself, right? Okay. So what is the importance of the molecular weight? Go back again to there. What is the relation with the strength and everything? Is it the bigger, the better, the stronger, or how is it?
Andy, do you want to answer it?
Because later on you will maybe you will make different types of polymer, right? By accident or anything, and the process, right? Then you can, let's say, publish a paper that the size of this is better than this because of this and that. So I think that's the one of the purpose of this experiment, the research. Before
I
we
think
talk about the benefit, yeah.
I think the higher the molecular weight is, it will increase the um, chemical resistance, which will increase the strength.
Do you think it's going to be better than smaller one when you apply this to the real application as a suture?
Um, I don't think the I mean the higher the better, but don't be too high, I guess, because we want to make a biodegradable one. So I think it should be enough around around 8 Newton tensile strength, I guess.
Okay. Any other explanation from the colleague, your friends? Before we move to the next question.
Yeah, what Andy's answer is correct. It should not be too high because it's gonna be so tough, and because it is we cannot shape it because the sutures is for shaping, right? And but it's don't be too low because the function of the suture itself is to bind two tissues together. But if it's too mm, I'm sorry, rentan. It's too apa bahasa Inggrisnya? Um, ya rentan.
Agile.
So yeah, so it will break easily and will not hold the tissue well until it healed. So it can be considered as bad if it's too low the molecular weight. So because and other answer is because the molecular weight, the higher the molecular weight, it will determines also the degradation time. So when it is higher, so means that the degradation time will be lower. On the other hand, when it is lower, so uh, it means that the degradation time will be so fast, and it's not really good for the sutures as a suture's characteristic like that.
Okay. 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 What about the water content? Did you do any measurement? How many percent water in the your product? Will it affect also the quality of your final product?
Of course, it will affect the final product, especially for the condensation, uh, polycondensation, because when we're using that step, that means that to make the molecular weight become higher, um, water will disturb the process, and it will make the molecular weight become lower. So we need to remove in the process, we need to remove the water. So the molecular weight become higher like that.
Okay. How would you do biocompatibility and biodegradable tests later on for this
Yang
product?
lain, um, do you want to answer it?
Because eventually you will do this also, right?
Oh, so it's actually we haven't really thought about that because our main focus is still apa getting the right PLA and making it into the suture. But I guess if we're going to test it, and we use the in vitro test with the bacteria.
Do you think
And
it will need preclinical study or maybe later on clinical study, clinical trial for this kind of product?
Yeah.
That will be my last question, Badidi.
Yeah, it will be because it's all somewhat new. It's still new because usually the PLA used is the synthetic one. So of course, before it's used widely, it will need some clinical study first, I think.
Just interesting to me, Badidi, why they call it is synthetic, yeah. Padahal this is literally derived from
Natural product.
natural product, yeah.
Yeah. Anyone of
Why
you
is
can
can
answer
you
that?
yeah, can you explain? Yeah. I know you do some engineering there.
Synthetic is because we should process it. Jadi it's not really the banana ham, I guess. So we should process it from starch to glucose and then to lactic acid and then to polylactic acid if it's natural. Some examples are like silk, cotton, catgut, collagen. Yeah, maybe it's directly, but if it's synthetic, it needs to be processed. It should have processed dulu gitu.
Because there are a series of chemical reaction, right? That's I think that is the reason why it's called synthetic. It's not really starch because the origin is starch, right?
Yeah.
But then they change this into acid. I think that's what make this be called as synthetic. Yeah. Oh, that's interesting. Okay, thank you, Badidi. I think that's should be enough from me for now.
Thank you, Pak Khalis. Okay, I have several questions. First is that why banana ham? If you show the slide that banana has many parts, yeah, and I think all of them contain what do you call it, the glucose as well, and so what can we not use the same technique to also make PLA from the other parts of banana?
Yandi want to answer it?
It is because we were um concentrate it to the starch in order to produce PLAs. So we use the stem, however, the banana hump. However, I don't think that will the fruit and flower will also have that amount of starch, which is around 76% starch.
So you are
So
sure,
that
yeah, the other parts do not contain that many starch as the stem.
um,
You are sure about it. That the other parts do not contain as many starch as the stem.
um, yeah, and yeah.
What is? How can you back up this information? Where is it from? You do the chemical analysis
No,
yourself, or
no.
Actually,
Actually,
there was a previous research done, and they used
Mm.
this banana ham as the material to make starch. So yeah, there are also the steps, and I think it's quite promising. So we use that step to and which we use the banana ham for to take the starch from.
yeah. Why I was asking this question, because in terms of sustainability, right? If you take the ham, it means that you take the whole banana tree basically. Okay, the whole banana tree will be dead. Okay, so but if you take the leaf, for example, the banana tree, it will still be alive and maybe can still produce other leaf afterwards. But if you take the stem and the pseudo stem, yeah, it means basically you are taking the whole tree. So how, in terms of sustainability, what is your opinion on that? How can we have a sustainable banana ham production to support your PLA production?
Um, Actually, I was when I was going to take the banana hump, I was searching it at Google, and there are lots of videos says that from one banana hump it will be equals to 16 banana trees. So from this we can actually perhaps cut it into a half, and the half of them we can use it to cultivate the tree, and the half of it we could use it to fabricate the suture.
Okay. Next question will be compared to other starch resource, yeah, as you mentioned earlier also, and emphasized by Pak Holis regarding the mangrove. How would you compare the starch content between banana and maybe other starch source like mangrove and maybe other plants?
So actually, we did some reading about it. So we compared the banana ham to other plants such as corn and wheat. Wheat, is it wheat? Yeah, gandum. Yeah. So the banana ham has about more than 70% content of starch, where the others is less than that. That's why we choose banana.
Okay. Okay. Next question regarding the process that you have been doing. So until now, what you have done is hydrolysis, right? The hydrolysis is what is the source and what is the product in the hydrolysis process.
The source is starch. We hydrolyze it into glucose, a monomer of glucose. So what we are aiming is to obtain glucose from here, so that it could be furtherly fermented by the Lactobacillus bulgaricus into lactic acid.
Okay. So it means that from the start isolation, you make hydrolysis in order to obtain glucose. Then after which you try to make the lactic acid monomer, correct? Using the fermentation.
Yes.
Can you please explain what does the bacteria do to make the glucose into lactic acid, and why do you need to use that specific Lactobacillus bulgaricus to do this fermentation to produce lactic acid? Yeah, anyone
So,
can.
Tanita, want to answer it?
Not really see, but I think
Okay.
a reason I have also searched that Lactobacillus bulgaricus is quite specific. It only ferment glucose, fructose, and lactose, if I'm not mistaken, into lactic acid. So yeah, I think maybe that's that's reason why actually we use Lactobacillus bulgaricus because we based it on a research that was done before. They also use Lactobacillus bulgaricus, but maybe that could be one of the reason why Lactobacillus bulgaricus was used.
Yeah.
And I also read a paper that Lactobacillus bulgaricus, so the authors test each of the many bacteria that they use, and they found that Lactobacillus bulgaricus produce 76% starch than others bacteria. So um, I think that's why lactobacillus is used, because they produce more yield than other bacteria.
Is this bacteria easy to find?
Yes.
Can you easily obtain it to do the fermentation?
Yeah, we already buy it.
Right. So if you compare with other bacteria, maybe let's say, for example, the one that is used to ferment, to do fermentation of uh, maybe rice or ketchup, from soybean, to make ketchup. Can you not use the same bacteria, maybe which is maybe more widespread?
I cannot confirm that we 100% can use it, but if it's about the fermentation and maybe we can use it because it also fermented the soybean, right? But as I mentioned before, the yield is not as big as the Lactobacillus bulgaricus produced. So um,
Can you
yeah,
explain it from the enzyme point of view? What enzyme does this Lactobacillus residus have, which maybe the other bacteria do not have? That makes more lactic acid, lactate. Have you read more about the enzyme that it has, that this bacteria has?
actually, when we're talking about breaking down the large saccharide to glucose, that means maybe it is amylase, right? Amylase.
That is during the hydrolysis, right? But now
Yeah.
from the hydrolysis, you already obtain the glucose and you want to obtain the lactic acid, La, and you use this fermentation process, yeah, like here in the slide, anaerob process using enzyme from microorganism to break down complex organic chemical to be simple product. So what are the enzymes there in the lactobacillus residus that make it to be able to produce more lactic acid compared to, for example, bacteria used to ferment soybean into ketchup, for example, or into other products. You haven't read that detail to the enzyme in that bacteria.
For me, it's no. To be honest, kalau yang lain.
Same here.
No.
Okay, no problem. If you haven't read it, just say yes. We don't know.
Yeah,
No, we don't know like that. Yeah, it's okay. No problem. Yeah, we cannot know everything. It's okay. Don't just be silent. Yeah, just say no. I don't know. So you haven't done this fermentation stage, have you?
Yeah.
Not yet. Okay. So, but you are going to do it soon, right? In the near future, despite the lockdown, you can do it at home. Is it possible?
We're gonna discuss it later, sir.
Yeah.
Yeah.
If any of you has enough yards in the house, maybe you can use part of the yard to do the fermentation. And for the incubator, maybe I would suggest to use off-the-shelf incubator. Yeah, I just see Tokopedia and I saw a lot of options, yeah, of incubator for eggs, for chicken eggs. Maybe you don't need to really make yourself to save time. Okay, so that then I think you will need. I don't know how high temperature it can be, but I think you need maximum 160 degrees Celsius, right? Maybe for the incubator you mentioned in your process.
45, I think.
At least for this PKM. Yeah, for the glucose fermentation.
And then 80. We also need the 80 degrees.
80 degrees, 45 and 80 degrees. So not that high, right? So should be possible with commercially available incubator. Yeah. Maybe I'm not sure because you have lockdown. If you already have all the basic tools to do the experiments at home, yeah. Otherwise, maybe we need special appointment just to grab or to borrow some of the materials from or equipment from the lab, which can be brought, of course, to home. Yeah? Not the big equipment. And yeah, the incubator, they are available also, small scale incubator from Tokopedia or something like that. Okay, so that will be all for the group session. Thank you. And we will have, I will stop.